Welcome back. This is Module 5 of GIS Primer, Geography 385. We're going to talk about the vector data model in Module 5 and actually in Module 6 also. So far in this course we've spent a lot of time kind of dealing with the important but maybe a little bit tedious aspects of GIS. First module was about systems and models, kind of a high-level view of what GIS is about. Then I talked about georeferencing. That was that stuff with the ellipsoids and geoids and projections and the concept that maps are distortions of reality. Then I talked about cartography. Cartography involves a communication process where you're telling a geographic story, and in order to do that well you're going to use a map and you're going to use cartographic language to make that map. And then last module was about metadata and data standards, which is all about making sure that the data that you bring into the GIS is as good as it can possibly be, and understanding what maybe some of the drawbacks of that data might be going in, so that when you bring the data in you don't expect things out the other end that you can't get. So now we're going to talk about the vector data model. I've already talked a little bit about this, so I'll quickly review the basic concepts. The vector data model is good for discrete entities, so when you represent reality as a collection of discrete entities, you should use the vector data model. And there are three different flavors of entities. There are points, lines, and polygons. So assuming you have this reality that has a stream and a lake and a forest and a bunch of ag and some urban in the real world, you can represent that in the vector data model using points, lines, and polygons. And so in this case the lake is depicted as a polygon. Notice that a polygon is made up of a bunch of points. And a polygon is similar to a line. A line is made up of a bunch of points, but in a polygon the line closes in on itself, which is called closure. These yellow points will become more important. I'll talk about them later. They're called nodes. The bluey brown points or the red brown points are called vertices. Okay. Points. Here's an example. Weather stations in Utah. This is from your text. A point is described by a location in space. So in this case the location is the longitude and the latitude. These would be what are called geographic coordinates. These aren't projected coordinates, so these are still mapped on that three-dimensional globe and somehow projected onto the map that you're seeing here. So a point is specified by its coordinates. X, Y, sometimes Z. Remember, Z from georeferencing involves geoids and estimates of elevation above mean sea level. Okay, a point doesn't have any size, so a point is zero-dimensional. Now a lot of times people will think of dimensions as how many coordinates are required to describe the location. That is a different dimension than this dimension. This dimension is a size dimension. So a point doesn't have a size, so it's zero-dimensional. Okay, lines. Looks like lines are made up of points. I'm still seeing points here, but I see yellow points and I see red points or brown points. And the distinction is the terminology of the yellow points are nodes. Nodes appear at the ends of lines or where line segments intersect. So ends or intersections are called nodes. The other intermediate points are called vertices, and that's what a line is. Basically it's a bunch of points that are connected to each other. It has one dimension, and that dimension is length. So a line is one-dimensional. In certain GISs and in advanced things you can actually draw curves between the points, or you can connect them with straight line segments. You can do it either way. ArcGIS is going to default using straight lines between these two things. Generally that works pretty well as long as the points aren't separated too far. Here's an example of lines, major roads in Utah, and you can see here we have a line which appears to be going through here. It's got yellow points, nodes, which would be endpoints or intersections. So in this case these yellow points here are intersections with other lines. These points here are vertices, and if you've ever driven out by Bonneville Salt Flats in western Utah, you know that there really isn't a lot of roads coming into the interstate out there, and so these might be exits that just are easy off, easy on exits, but really they're not intersecting any roads that go anywhere. Similarly, on I-70 you can see there are a bunch of nodes, a bunch of intersecting roads, and only a couple of those vertices that don't intersect another line. Polygon. Polygon also appears to be made up of points, and it also has nodes and vertices. A polygon is basically a line that closes in on itself. So the starting point and the ending point of a polygon are the exact same location, and that's required. That's called closure. That's one of the characteristics of a polygon. If two polygons share common boundaries, the places where the polygons intersect are actually nodes. So if I started my polygon here, this would be yellow. These would be yellow because it's intersecting another polygon, and this is just an intermediate vertex because it's not intersecting anything. Areas or polygons have two dimensions. They have the dimension of area, and they also have a dimension involving the perimeter around the polygon. And polygons that share common boundaries share nodes. Here's an example again in Utah. These are counties in Utah. This is Emery County that's illustrated here. Looks like we have nodes, and the nodes appear where there are intersections between Emery County and adjacent counties. So where they share a common boundary but there's not an intersection of uncommon lines, then they're just going to be vertices. And notice that you want Emery County to exactly match the boundary of this adjacent county in here. And so there's one other aspect of the vector model I need to talk about, and that's topology. Topology is going to allow us to make a rule that says Emery County must share the exact same border as this adjacent county in this area. So what's topology? Topology is the study of properties of geometric forms that remain invariant under certain transformations as bending or stretching. Now the way I like to think of this is if you have a map that's drawn on a sheet of rubber. As long as you don't tear that rubber, topology applies to anything that even if you stretch or bend or fold that sheet of rubber, the map is still going to have those same topologic properties. And so there are three different types of topology that you need to keep in mind. One is adjacency. So that would be those adjacent counties in Utah. They have to share exactly the same boundary. You can imagine if one county's boundary went into the others and there were overlap, then you'd have issues with which county does someone live in if they live in that overlapping area. So adjacency is one of the aspects of topology. Enclosure is another one. Let's imagine you had towns inside of counties, and a town can only reside within a single county. And so you can make a topologic rule that says a town can only reside in a single county. That's enclosure. So polygons can enclose, or points can be enclosed by polygons. The third flavor is connectivity, and that one applies basically to lines. You would want connectivity if you're ever going to use a network. Getting from point A to point B, you're only going to be able to get there if the line segments are connected to each other. You can also make a connectivity topological rule so that when you draw a road system or edit a road system, you don't have overlaps so that a road just dead ends in the middle of nowhere instead of stopping at an intersection, or undershoots where a road doesn't get to the intersection, it stops before it gets to the intersection. So those are the three elements of topology: adjacency, enclosure, and connectivity. Okay, so based upon these basic concepts, points, lines, polygons, and topology, we're going to be able to start using the GIS to take this data that I spent all these weeks talking about and you spent learning about, and transform that data into information. And that's where we're going to start moving in the next videos. So next time I'm going to talk about data structures, how we store this vector model data inside the computer, and a little bit about the terminology so that when I start using these terms, you'll know what it is I'm talking about. So that'll be next time. Thanks.